So now that we have our definition of a derivative, both at a point and as a function, there are a number of things we need to talk about. We need to talk about some notation, a definition or two, and we're also we're going to spend a lot of time over the next 5, 6, 7 sections talking about functions that are differentiable and how you can find their derivatives. So in this lecture, I want to talk just very briefly also about functions that are not differentiable and how you can recognize that situation. So first, I want to talk about notation. We've seen a couple of these already. We've seen this prime notation, right? This f prime of x and y prime, depending on if we're explicitly talking about a function f of x, or if we have more formula like y equals. There is another way we write this. We sometimes write this with this dx notation here. And you notice we have two versions of this as well. One for when we're talking about a formula, like y equals, and another when we're talking about a function. And sometimes we don't really have a function. Sometimes I just want to differentiate an expression. And I know some purists are going to just cringe to hear me say that, because functions are the things that we differentiate, and yeah, okay. But sometimes I just want to know what the derivative of something is, right? I want to know what is the derivative of x squared plus 2x, and this dx notation gives me a really quick way to say, look, I just differentiate this thing, right? And then finally we have this notation here with the little dot over it. It's a little archaic. You don't see it very much anymore, but it does show up occasionally, mostly in textbooks. So I didn't want to include it just so, if you ever do run across that, you know what they're talking about. Okay, so here is just a little terminology. All right, a function is differentiable at a point A if f prime of A exists. Right, so differentiable is just the word that we use to describe a function whose derivative exists. And we can talk about it either at a point, or we can talk about it on an interval. The terminology is the same. In both cases, we refer to the function as being differentiable. So if you think back to when we talked about continuity, we had this notion of continuity from the left, continuity from the right, and just continuity. We have the same situation going on here with differentiability. We can also talk about a function that is differentiable from the right. So we've got that little plus sign here. And that's differentiable from the left. So we've got a little minus sign on this one. And the expectation is the same, right? For the function to be differentiable at A, these two limits have to be, they both have to exist, and they have to be equal to each other. Okay, so let's use this. Now, I want to see, like I said, we're going to spend a lot of time talking about functions that are differentiable. So let's take a look at this thing. Right, f of x equals the absolute value of x. Right, if you sketch this, hopefully you're familiar with this graph. It has this kind of V shape. And intuitively, hopefully you kind of realize immediately, x equals 0 is a point that I'm concerned about. In a neighborhood of any other point, this function is just a line, and the rate of change of a line is just the slope, and everything is fine. Right, but what's happening at x equals 0? Well, let's see. First, just so we're clear, referring back to our left and right derivative formulas, a is 0. All right, so what I'm going to get here is the right. Let's do the right one first. The right-hand limit is the limit h approaches 0 from the right, f of 0 plus h minus f of 0 all over h. Okay, now remember, we're just looking at the right-hand side here. And if we just look at the right-hand side, this function is described by the equation y equals x. All right, so that means this is the limit h approaches 0 from the right of 0 plus h minus f of 0, that's 0, all over h, and that is just 1. Okay, well, that's good, right? That's consistent. It matches what we already know about the rate of change of the line on that side. So now, let's try the other side. This is the left-hand limit. This is the limit h approaches 0 from the left of f of 0 plus h minus f of 0. Really is the same formula over h. Now what's happening on the left-hand side? On the left-hand side, this graph behaves like y equals negative x. All right, so that's the formula I'm going to use over here. This is the limit h approaches 0 from the left of minus 0 plus h minus 0 over h. And that numerator, this numerator here simplifies to minus h. Minus h over h, that's minus 1. Yeah, there's a problem. The left and right hand limits are different. That means this limit, the limit h approaches 0 of f of 0 plus h minus f of 0 over h, does not exist. Because that limit is the derivative, that means that the derivative does not exist at x equals 0. Okay, so how can we just kind of generalize this? In general, where is a function not going to be differentiable? Well, a function is not going to be differentiable any place where it's discontinuous, any place where it has a gap. It's not going to be discontinuous at any place that has a sharp corner. That's what we saw with the absolute value of x. And it's also going to be non-differentiable. I think I may have said discontinuous there with a sharp corner. I meant differentiable. It's not differentiable if it's discontinuous. It's not differentiable if it has a sharp corner like the absolute value of x. And it's not differentiable if the function has a vertical tangent line. We'll actually see some of these a little later on. Functions that have roots in them, like the cube root, for example, they sometimes are going to have a part that looks like this. It's going to come up, come to a point, and come back down. The tangent line at this point, technically it exists. This function does have a tangent line at this point. It's just vertical, right? And you know, you refer to your algebra classes, right? The slope of a vertical line is undefined because the slope is the linear equivalent of the derivative. That means the derivative is undefined there as well. Okay, now here we have a nice little theorem that you should certainly be aware of. Differentiability implies continuity. If a function is differentiable at a point, then it is continuous at that point. And I want to prove this. The proof is actually pretty straightforward. I'm assuming that the function is differentiable. That means I know that the limit as x approaches a, let's make that the point that we're talking about, of f of x minus f of a over x minus a equals L. It exists. I'm not going to really use that number. All I care about is that the limit exists, right? And what I need to show that, to show that it's continuous, I need to show that the limit as x approaches a of f of x equals f of a. So this is what I know. This is where I need to end up. Okay, so here's how we're going to do that. All right, let's look at the limit x approaches a, x approaches a of f of x minus f of a. Okay, well this equals the limit x approaches a of x minus a times f of x minus f of a over x minus a. I just multiplied the top and bottom, right? I kind of implicitly made this into a fraction here. And then I put x minus a on the top, x minus a on the bottom. Just like we were finding a common denominator if we were adding two fractions. Okay, now I'm just going to apply a bunch of limit rules. I'm going to split this up. This is the limit. Well, let me go back to blue. This is the limit x approaches a of x minus a times the limit x approaches a f of x minus f of a over x minus a. Okay, this limit, and you can pull out the definition and show this in detail if you want. This limit is just a minus a, which is 0. This limit, that's f prime of a, right? Which I know exists, right? Because that was my assumption. If you like it, I said I wasn't going to use it, but if you like, you can put that L in there, right? So this is 0 times L, which is just 0. Okay, that's going to give me what I need. Now, go back to the left-hand side and apply our limit rule here. I'm going to split this up. This is the limit x approaches a of f of x minus the limit x approaches a of f of a. Move the f of a part to the other side. The limit x approaches a of f of x equals the limit x approaches a of f of a. But f of a, that's just a number. It's a function value, right? It's a number. So this is equal to f of a, and that is what I needed to show. Right? So you see here, all right, differentiability implies continuity. A differentiable function is automatically a continuous function. Now, obvious question to ask, is the converse true? Does continuity imply differentiability? Well, no. And we saw this on the last slide. Right? F of x equals the absolute value of x is continuous at 0. Right? The limit as x approaches, let me write it, the limit x approaches 0 of the absolute value of x does equal the absolute value of 0, which is 0. Yes, it is continuous there, but as we saw, it is not differentiable there. Okay, so one last kind of general statement here. We can do higher derivatives. I'm gonna mention this just briefly here. Then we're gonna set this aside. We'll come back to it a little later on. If f prime of x is the derivative of x, right? Derivative of f of x, then it's a function. It means I can take its derivative, right? And the way we write that, f double prime of x equals the derivative of f prime of x. And the language I would use here, I would say this is the second derivative of f of x. And obviously, we can keep this going. I can do f triple prime, right? That's the third derivative. Once we get up to 3, we stop with the little hash marks. Okay, when it gets with 4, it starts to get a little crowded up there on top. At this point, for anything higher than 3, I would put fn of x. That is the nth derivative. Okay, so a lot of talk there. I know, not a whole lot of calculation going on. For really all of the remainder of this chapter, the next 10 lectures or so, we're going to be focused on finding derivatives. If I give you a function, how can you find that function's derivative?